All right.
It's not coffee. Don't drink it.
Ladies and gentlemen, class recording has started, so just keep in mind that any discussion relating to this class or otherwise is being recorded, especially if you're sitting close to the microphone. If you want to continue to complain about something that somebody made you drink that was under false pretense.
Don't drink it.
The first part.
Don't do it.
All right. Once again, class recording has started.
That's like my words start
It'll
over.
be out there for everybody to listen to. That you know.
Selecting my words here.
All right. The beginning of this unit. The beginning of this unit, it will be. So if you want to check it out,
I'm gonna check out the first 5 minutes.
The beginning of this unit, we dealt with rotational motion, and the first thing that we talked about was measuring rotational motion. So we talked about displacement, velocity, and acceleration. And then we made our way to torque. And we talked about torque being the chain or causing a change in the rotational motion. But then we talked about a special situation dealing with torque, that being equilibrium, where all of those torques balance, so there is no change in rotational motion. But that doesn't always happen. That sometimes we get angular acceleration, right? The rate of change of angular velocity, that's going to be an object either rotating faster or rotating slower. And we define angular acceleration as the change in omega over the change in time, right? Delta omega, change in rotational velocity over change in time. This is just an old definition, angular acceleration, changing how fast something is spinning, either making it spin faster or making it spin slower. Tell it. Hold on to that so it doesn't fall. Go on the side. All right. So yesterday, we had our first example, or at least measuring our first example, of angular acceleration. The first lab that we did in this section was the lab of the arm, right? And we had several forces acting on that rod, but they were all balanced because it was just sitting there horizontally. And then you did the meter stick, where you were moving the objects around the meter stick in order to balance it out, once again, not rotating. But yesterday, we set up a situation where a force was acting on this object and causing it to rotate, right? So Tyler and I are going to let these go at the same time. I'm going to give you a 1, 2, 3, go, all right? And then we'll observe differences here. Okay, ready? 1, 2, 3, go. Just going back up.
Okay, cool.
All right, so. Now I gotta fix that elaborate prop for next class. All right. First, was the torque on either of those objects balanced? No, because they're spinning, and as they were spinning, faster, 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 faster. But we saw some definite differences in how they were spinning, right? Tyler's was spinning faster than mine. That caused his rope to unravel quicker, and that caused his mass to get down to the table faster than mine did, right? More angular acceleration on Tyler's than mine, okay? We talked about the idea that torque causes changes in rotational motion. So if we have an object like this that has a single torque acting on it, okay, it will cause angular acceleration. That object will experience angular acceleration. It will change how fast it's spinning.
Oh, question. That was like the one on the quiz. Which one would be? Which one had the more torque?
There's some people who haven't taken the quiz yet, so I'm going to say, hey,
That wasn't on the quiz.
Technically, this picture was not on the quiz.
Well,
so, technically, let's go with the technicality at this point. So.
All right.
So this object will experience angular acceleration. And
Blew it.
consistent with what we talked about previously, a larger torque is going to produce greater angular acceleration. There is a direct relationship between torque and angular acceleration. Tyler's experienced more angular acceleration because his wheel had more torque on it. If we look, right, these masses that were hanging off, go ahead, finish writing, sorry. While you guys are doing that, I'll set up the next demo.
How many balloons do you think it would take to make the cut?
That's what you're figure it out, right?
What?
Quite a
Not
bit.
really.
Take quite a bit of balloons.
Okay.
I mean, this is a class that asked that question.
It really is. I mean,
I
We
know.
could probably figure it out too.
I'm not gonna ask it in English class.
no.
No.
All right. So you are going to have to actually move those for a second so we can do this next demonstration because people got to like see it. Okay. Does it make sense that Tyler's wheel was spinning faster than my wheel?
Yes.
Okay. More torque on Tyler's wheel because these masses here, right, they were the same mass. These are both 50-gram masses. So the force that was being applied to both of those wheels was the same. But what do we see about where Tyler's force is applied versus mine? Bigger lever arm, more torque, more acceleration. Direct relationship. Okay? But that's not the only factor, right? Just because we push on something harder, does that mean it necessarily will accelerate more than another object?
No.
No, there's also another factor. What factor goes into acceleration as well? Heard someone. There's a mass factor as well, right? The lever arm goes into like the torque, right? But just because we apply the same torque to something doesn't necessarily mean that they will experience the same angular acceleration, okay? So here are two round objects, okay? These round objects both have the same mass, and they both have the same radius, okay? But one is made out of wood, and it's solid. This one is made out of metal, and it's hollow. They have the same mass, and they have the same radius, but how that mass is distributed is not the same. Does that make sense?
Yeah.
Okay. This is all nice and solid. All the mass for this one is out on the end.
Metal's gonna win.
So, let's try it out. So if we talk about torque, right, gravity's going to cause a torque, and it will cause these objects to start spinning. Because they're the same mass, how much gravity is going to be acting on them? The same. Because they're the same radius, what would we say about the torque?
It's the same.
Same as well, okay? But, as we'll see here in a second, Tyler, you think metal's going to win?
Should it win
I
because
kinda
all the
feel
mass is on the outside?
Well, let's talk about it. Well, let's find out, okay? Are we ready?
Well, are we gonna
Might
talk
need
about it
some,
or find out?
Tell me.
We're
Give me ideas.
Can we find out and then talk about
So
it?
so there's really only two. There's really only two options, right? Tyler thinks that the metal one's going to win because the mass is all set on the outside. Say again.
Is there air resistance?
Limited, especially because they're both moving in the same direction, so they're both going to encounter the same air resistance, you know,
Wait,
that
so
way.
maybe they'll both be the same, is that an option?
They have the same mass and they have the same radius, so they're experiencing the same torque, right? Torque causes them to spin, and they have to spin to go down this ramp, yes? Sure. I mean, that's how they're going to move down the ramp. Okay. These are all valid questions. So here, all right, are we ready? 3, 2, 1, go.
Oh, Tyler. Gosh, I told you.
Okay. So we see that same mass, same radius doesn't necessarily equate to the same acceleration. Alright? This one won, right? solid disk, solid sphere. Okay? They don't weigh the same, right? So there's a difference in how much mass there is, but that also means there's a difference in how much torque there is as well. Okay? So now here, this is a smaller radius and a smaller mass, meaning how much torque should this one experience? Less torque, right?
I think the marbles gonna win.
Okay.
All right. Well, I'm gonna go with the other thing because that is.
Also, yeah.
All
They're
right.
gonna be like the same. Probably gonna be the same.
All right.
You might want to move.
No, because the marbles gonna be this.
Here we go.
Ran it over.
It did run it over, but the marble got in front of that one, right?
Cut it off.
Well, it did cut it off, which means it was going faster. Okay.
I don't know.
So,
I don't believe you.
you want to see it again?
Yeah. Can we spread the marble out? Sure.
And then also isn't complete sphere.
Yeah, it's not actually a complete. It's got a little hole in it. So. All
Alright,
right.
you're just messing everything up.
Yeah, I don't know. I believe you.
This is the relativity discussion all over again. So.
Let's not go back there. That was
I
some
didn't
hard
enjoy
times.
that.
It was like the worst 2 weeks of my life. All right, here we go. It's a marble, by the way. Totally
Yeah.
solid, no hole in it. Okay. All right, here we go. 3, 2, 1.
Really not that they're even.
That's what I'm saying.
Wrong.
The big mess with.
No.
No, because the small.
What?
No.
What are you talking about?
Well, the first time this one got in front of
Wait,
it,
but shouldn't
Yeah.
the wooden one
Hit it.
win because it has a bigger
The wooden one won.
arm?
Now,
then this one
Like,
didn't.
it does have a bigger lever arm, but there's
Oh.
definitely some differences in mass,
Here, Amani has two over here, man.
and there's also some difference in torque as well.
That's still heavier than this, right?
All right, so what does that mean? What we start seeing is that how our mass is distributed will affect the angular acceleration. Another example. So, metal rod, 2 metal weights in the middle, okay? And I take it and I hold it like this, and I can shake it just like this.
Yes.
No problem. Of course. Okay? But now I slide these out farther. Okay? Am I going to be able to move it as fast as I did before?
No.
Okay?
I saw the
I'm glad I backed up.
That would have hit really right in the face. That would have been funny.
Well, it's
I'm an English.
Okay, well,
Teleportation.
that's what a Mel Kiper's down says. All right, so if I move it a little farther out, right? Okay, not quite as
I
fast
feel like you could. You just
in terms of this. Okay, or let's go this way. Okay, I'll slide them all the way down here to the end. Okay, and maybe people in the back can see if you know there weren't like 14 balloons in the way.
Hey, you want me to try?
So if I take this and I try to balance it on my finger, okay? So I take this one, balance it. Okay.
Don't hurt yourself.
This rod's really light, so balance, okay? But if I flip it over now, same mass, right? But
Were you even trying before?
what do you want to do?
I know.
Come on.
All right.
I like proving you right.
So what we find out is that
Do it. Let it go. Let it go. Let it
what
go.
we find out is that it's not just the mass. It's not just the mass that affects the angular acceleration.
No, it's fine.
It's five, guys.
5 for 1.
Shannon, we need a lot to get that count down.
I know, you're putting like
You're
20.
Yeah.
Try like, okay, go up today, I'm gonna just go like
So the next topic that comes
Yeah,
up out of this is called the moment of inertia. inertia. I know it sounds. Ooh, it sounds so fancy. It sounds like physicsy. Okay. The moment of inertia is also referred to as rotational inertia. So what we find out is that just like mass, it is in an object's nature to resist changes in rotational motion. Too much up force. Unbalanced force, upwards acceleration. There it is. So.
Damn, I missed it.
Physics in action, everybody. It really works. So.
I wish the people listening to this could see like a video of
I know, video would make this way better. But
They have no clue what's going on.
yeah.
For those of you at home, we just made a permanent marker float using balloons.
Thanks for explaining it was a permanent marker. Because if we just said marker, I don't think they would have got the
They
picture.
They have a better visual of it now.
It's a Sharpie.
I like one of my
Fine tip, sharp.
Sorry, fine tip, black Sharpie, okay?
So what we find out is that
I love how I turn to look at it.
the moment of inertia, or the rotational inertia, same thing, those two terms are used interchangeably, depends on two things. It depends on the mass, but also the distribution of that mass around the axis of rotation. So not only how heavy is something, but where do we put that mass? No, I'm just. I was like, I'm waiting for people to write things down, because some people are actually writing things down. So.
You know he's not
Those
taking
people,
notes.
those people not whose view is not obscured by balloons.
Happy guys? Just let it in the air. I think I see over it.
That's what I'd say. If you just
Oh, wait,
look at the
right
ceiling,
with-
everybody
right
will
with
see,
that
like,
marker.
no problem. So
Shane, just let it go.
yeah, if you just let it go, everybody sees, no problem.
We're good.
You should
But
write-
it's
you
still,
should
but
write
it's
that
still
down.
festive in here. So.
Use a marker for my nose.
So, if we go back to our hoop and disc race, okay, as they're sitting up here at the top of the ramp, are they rotating?
No.
No.
Not yet.
Rotational inertia, or moment of inertia, says that if these objects aren't rotating, they want to continue not rotating. Just like an object at rest wants to continue at rest. So, the object that wins is the object that has less rotational inertia, because it's easier to get it to roll down the ramp. The object that loses has more rotational inertia, because it's slower to get moving. Alright? So what we find out is that mathematically, we calculate the moment of inertia based on a couple of ideas. Now, this is for a point mass. This is for a point mass. This just being like a single spot on the end of the string or something like that. The moment of inertia depends on mr squared, where I represents the moment of inertia, m is the mass of whatever object we're looking at here, and then r is how far away from the center we are. So in this picture, that would be like the length of this string. That's if we're calculating the moment of inertia for a point mass, for just a single solid object. That would be fine for something like this, the rod with the masses on it, because this mass is, the rod is real light, these are much heavier. We could take the mass of these two objects, the distance from the point of my finger, that would be the moment of inertia for this object. But what we find out is if we have an object like this, a solid object, there are several masses, right? Each one of these little molecules that makes up this disk has its own moment of inertia. And all of them have different radii. So there has to be a way to account for all of those things. And there is, it's calculus. So basically what you do is you take the integral
Oh, I love
of,
that.
You take the integral of the moment of inertia of all of these point masses. You don't have to do that on the test, okay? Because what happens is, when you take the integral for objects that have different shapes, we find that formulas start showing up based on that shape. Okay? For a ring, a hoop, like this, the formula looks similar to the point mass formula because what do you see about all the mass? How far is it from the center of rotation? It's all far, but it's all the same. So this is just a bunch of point masses that we've added up. Okay? But if you look at something that's a solid disk, uniform disk or cylinder, you take the mass of this whole object times the radius of that object, but then you take half of that value, 1/2 mr squared. Because some of those are farther away from the middle, some of those are closer, but when you integrate and look at all of them together, you end up with this formula. And then for a sphere, something solid where all the mass is evenly distributed around one central point, 2/5 mr squared. Okay? So based on these three formulas, which one would win the race down the hill? If we started them all at the top, which one would win the race down the hill? The sphere.
What is it, the disc, the half?
Yeah, but this is
Oh, okay.
less than half, right? So it has, so the uniform sphere has the least rotational inertia, meaning that it's easiest to get it down the hill because it wants to rotate, or it wants to keep at rest the least. That was terrible English, but hopefully you understand. What? That's, well, if we're comparing three things, right?
That's what we're running with calculus.
So if you do like a baseball,
Yep.
and like the other thing would fall.
Let me see that.
In theory, yes. All right. Now, Bridget, there,
Different math.
it's you know, in this case, yeah. If we're going to really get a good, accurate representation of this, we need to have objects that have similar masses and similar radii, right? Because we're only talking then about.
Let's go.
So stupid. It's so stupid stopwatches that I brought in here. Because we're talking about the torque caused by gravity, basically. All right. But when they're on this ramp, there's other torque. It only goes like for a minute.
I was gonna say, should we
Come on, guys.
remember, this is being recorded.
Sorry, Shada. Is that disrupting your educational flow?
Yeah.
It's not. Is that the glue you have hanging off your glasses?
Yeah, hello. I'd like to place an order for a pizza.
Let's see how many balloons it takes.
Yeah.
Six.
440-552-0679.
So where does this all culminate?
Yeah.
This all culminates with Newton's second law for rotational motion.
Two large peppers.
Newton's second law is something we've talked a lot about. Okay? The whole idea of sigma F equals m times a. That idea exists for rotational motion, but now instead of sigma F, we're looking at sigma tau, the total amount of torque that is acting on that object, is equal to capital I, that's an I, not an L, okay? That stands for the rotational inertia, or the moment of inertia for that object. And then that equals, so sigma tau is equal to I times alpha, where alpha represents the angular acceleration.
So say you had another force coming off of that
Yep.
wheel. Which angle would have the bigger torque? That 90
Well-
degree angle or the one maybe coming off like a
Well, if you know the formula for torque, right?
yeah.
The formula for torque has sine theta in it, right?
Yeah.
And for sine values range between 1 and -1, right?
Yeah.
Okay? 1 is the
90.
sine of 90. Nothing's bigger than that.
Yeah.
Okay? So if you have any angle either less than 90 or greater than 90, it would produce less torque than that force.
Nice. All right.
Hypothetically speaking,
Yeah.
of course.
Should have worked. Tyler.
Sorry. The person that matters for wasn't listening anyway. So. All right. Are we good with this idea?
Not at all.
Not that idea. This one.
Yeah, I know.
All right.
Separating motion.
Hey, Bonnie.
Yeah.
Yeah, so, when we do problems for this,
Yep.
are they always gonna be either a ring or a sphere?
I will give you something solid. Yeah, something that you know the formula for. And I would give especially at the beginning, I would give you the formulas for those shapes.
Okay.
Right. So yeah, it'll be either be like a ring or a sphere or a hoop or a disc or something like that. So yeah, so it'll be one of those. All right, questions. So on Monday, we will start in on working on some problems dealing with this with these rotational Newton's second law, or working on the lab. Is that good?
I'm gonna be